This training will help you understand data fusion, a technique for filling in missing data on GOES17 when the ABI sensor saturates because of instrument heating. I'm Scott Lindstrom from SIMS. The Advanced Baseline Imager, the ABI, on GOES-R includes a loop heat pipe that moves heat away from the sensor. On GOES17, the loop heat pipe does not operate at full capacity, allowing solar forcing to heat the ABI instrument. The instrument changes temperature, which is a calibration challenge, and the individual sensors can ultimately saturate. The calibration challenge is mitigated by predictive calibration. Fusion supplies information when the ABI detectors saturate. The blue line in this figure shows a predicted peak daily focal plane temperature on GOES17. If the loop heat pipe functioned properly, this value would be mostly steady. During some times of the year, though, centered on the equinoxes, the sun is positioned so that it shines directly into the ABI at night, causing warming. Horizontal black lines show predicted temperature values at which individual bands start to lose integrity as the ABI warms. Band detection will saturate completely at temperatures slightly warmer than the black lines. Bands 13 and 14 at top are affected by the heating only during about a week of the year. Bands 10, 12, and 16 at the bottom will be affected for much longer. Weeks of data at each band are lost annually. The other infrared bands, 8, 9, 11, and 15, show outages in between the two extremes. This figure shows improvement brought about by predictive calibration. The figure compares band 12 in late July, at the start of the fall equinox heating period, and before band 12 saturates. The red line shows a difference between the mean GOES16 and GOES17 band 12 brightness temperature values in a region on the equator on July 25, 2019, before predictive calibration. The green line shows much smaller differences, a great improvement, on July 26, 2019, after predictive calibration was implemented into the GOES17 ground system. Excess heating in the ABI affects different bands differently. In this image from August 3rd, band 8 on top is not yet saturating. Difference values between the two satellites are small. Band 10 in the center is saturating for some times, and so is band 12 at the bottom. The number of missing times is different for each band. Here we see how the steady increase in the maximum focal plane temperature from August 1st at 91.42 Kelvin to August 10th at 96.49 Kelvin causes more and more data to be lost in band 12. On August 1st, perhaps 3 image scenes are lost. That increases rapidly so that by August 10th, more than 2 hours are lost. This image, I call it the watermelon plot, from Fred Wu of NOAA, compares data outages in red due to saturated sensors during the spring 2019 equinox heating season. Green regions show good data, blue and orange show data that are affected by warming but still usable. Band 10 in the center shows the longest outages during the 24-hour day spans plotted, and also the first and last effects as you get closer to equinox in February and farther from equinox in May. Band 11, in contrast, has much less data loss. The beneficial effects of eclipse, when the ABI slips into the Earth's shadow at night, are also obvious. When can you expect to see no data if you don't use fusion? Here's an example from an inspection of data in AWIPS for a day in August. As August progresses, the times the data become unusable become longer and longer. You'll see similar outages in February, April, and October. The fusion approach for restoring the missing data starts from the last full set of infrared radiances known to be well calibrated. We'll call that at time T0. Then at subsequent times, when cooling issues cause missing or bad data in the other spectral bands, the infrared window band 13 measurement for a given pixel is linked via a KD tree search to the 5 best matching time T0 infrared band 13 measurements. The other spectral band measurements associated with these 5 matches from time T0 are then averaged to estimate a restored value for each missing ABI infrared spectral band at the time T for that pixel. Thus the fusion of data from one time to the next is accomplished. Fusion uses the clean infrared window, and it does have limits. For example, if clear air turbulence develops, it won't be observed in long-wave infrared bands, so its presence will also not be in fusion water vapor imagery. Errors from fusion do increase with time, depending on how well correlated bands are with the clean window. Cloudy radiances are better correlated than clear ones. Errors in data fusion products mean that data fusion imagery should not be used in RGBs nor in level 2 products. Fusion is provided to give a guess at how the image would look based on its previous relationship to the clean window. Band 11 and band 13 are very well correlated as shown in this plot. Fusion should work well with band 11. Band 13 and band 10, in contrast, are not very well correlated except at cold cloud tops. Fusion errors will be larger in band 10 than in band 11. Here's the start of a series of images showing the operational GOES17 band 10 on the left and the data fusion version on the right. Overall, there is good agreement, but a keen eye will quickly start to find differences. Some are subtle, some aren't. 20 minutes later, GOES17 band 10 is starting to saturate. This is when fusion is going to be useful to maintain a signal. 20 minutes after that, there's even more saturation. And by 12:30 UTC on this day, the operational GOES17 band 10 field is unusable. But fusion, that is using the clean window and its earlier relationship between band 13 and band 10, is producing a signal. Artifacts in the fusion field, shown in the middle, can be traced to the band 13 clean infrared field shown at right. The best correlation between band 10 and 13 is the cold cloud tops, so that is where the smallest errors should be. The band 13 clean infrared window image shown here on the right has a different enhancement than the other two images that are water vapor images. Here's another example from February 2019. Fusion water vapor imagery in the center includes structures that exist in the infrared window channels that are not present in the water vapor imagery. A little later, you can still see that feature in the data fusion product in the center. It's not in either the GOES17 or the GOES16 water vapor channel image. This is a GOES17 low-level water vapor image, that's band 10 at 7.34 micrometers. It's the PACUS sector, from 11:26 UTC on August 14, 2019. This was just as the fusion products are starting to be generated on this day. The next image will be the data fusion image. You will note differences between the two images, especially in clear regions. Cold cloud tops, however, are approximated very well. An hour and 40 minutes later, during the peak in the heating of the ABI, the band 10 detectors have saturated and you get no information. Data fusion for the same time depicts a plausible but not perfect evolution of the field. Again, expect the cold cloud tops to be best represented. Here's the first band 10 image as the ABI detectors emerge from the saturated period. What does data fusion look like at this time? Differences between this scene and the next one you see will show good correlation in the cloud tops, and larger differences at warmer, which is darker for this enhancement, brightness temperatures. Here is the data fusion for the same time. Toggle between this image and the previous one. Cold cloud tops are captured pretty well, but there are differences at warmer brightness temperatures. You can find real-time fusion imagery at these links. The one on top combines band 10 from GOES17 and GOES16, and it shows most of the Pacific and Atlantic basins and the Americas. The one at the bottom shows individual bands for GOES17. Here's what the band 10 combination looks like without data fusion. And here's what it looks like with data fusion. Data fusion looks best for large-scale features. Some concluding thoughts. Fusion data fills in missing data from individual bands by relating the clean window infrared channel to the band that becomes missing. This relationship is determined when all bands are well calibrated. Then, when the satellite band saturates, that established relationship can be used to infer what the saturated band would be detecting based on the values in the clean window band. This concludes the training on fusion data. Thanks for listening.